Welcome to today's lesson. In this first tutorial, we will simplify nth root radicals and approximate nth root radicals on the calculator. So we are into chapter 6 and we're looking at section 6.1 and 6.2. We're talking about radicals now. So let's first talk about this symbol. We have our radical sign, this radical symbol or radical sign. We have a number or a variable or an expression that's underneath our radical sign, and that is called our radicand. The radicand is the stuff that's underneath a radical symbol. And then we have this other little number that's out here, and that represents our index or our root. Most of the times we're talking about a square root, so we don't actually see a number here. It's implied that it's a 2 for a square root. But if we see a little 3 or a little 4 or a little 5, then we have a cube root or a fourth root or a fifth root. And now that we have different indices is the plural of index, then we have to finish what our like radicals definition would be. Our like radicals, not only do they have to have the same radicand, meaning the same thing underneath the radical sign, we also have to have the same index. We cannot take square roots and cube roots and add them together. They have to have the same index and the same radicand for us to be able to add or subtract our like radicals. All right, let's talk about evaluating and simplifying. Evaluate means to find a value. The answer to an evaluate question will be a number. It almost has the word value in the word evaluate. If we're asked to simplify, simplify simply means to rewrite into a simpler form. Sometimes that end result is a number, but most of the times it will still have some sort of variable in there. Evaluate will always be an answer that's a number. Simplify may be a number, but usually it has some variables in the end. Okay, so let's evaluate or simplify. Square root of 64, well, that's pretty simple. We all know that the square root of 64 is 8. Square root of negative 64, it's a good thing we know complex numbers. When we have a negative underneath a square root, we know that that comes out as an I. And then we have the square root of positive 64, which we all know is 8. So this ultimately is 8I. This is not real. This is an imaginary concept. Watch out for negatives underneath square roots. How about the cube root of 64? I want you to get to know some of your cube roots, so I've given you a powers table that you can memorize. I've given you the first 20 perfect squares. You should be proficient with those. And I've given you the first 7 perfect cubes. And I've given you some fourths and some fifths and some sixths and some sevenths. Perfect cubes are right here, and I'd like for you to get to know them. 64. That's 4 cubed. 64 is not just a perfect square, it's also a perfect cube. Cube root of 64 is 4. Cube root of negative 64, it's okay to have a negative underneath a cube root or any other odd root. If you have an odd number of negatives multiplied together, for example, 3 negative 4s, that's okay. It makes a negative. The cube root of negative 64 is negative 4, and that is still a real number. It's just the even roots, a square root or a fourth root or a sixth root, that we have to watch out for negatives because those will be imaginary. How about the fourth root of 64? I don't know that many fourth roots, and that doesn't ring a bell. Let's look at our fourth root. Fourth root of 64, I'm looking at my fourth roots. I don't see a 64. 64 is not a special fourth root. So we cannot evaluate this unless we had a calculator to approximate. So maybe we simplify, because I see the 16. 16 goes into 64, and 16 is 2 to the fourth power. Okay, so I can deal with that. So let's say the fourth root of 64, I'm going to break that apart into 2 different fourth root symbols. 64 is 16 times 4. The reason why I do this is the fourth root of 16 is a nice number. The fourth root of 16 is 2. And then the fourth root of 4 will just stay like that. So I can simplify this one. I can't evaluate it because, yes, this is a number, but it's really just in simplified form. Let's put some variables into it. Let's talk about the cube root of 8x cubed. I'm looking at the number first. 8 is a perfect cube. I can look at my powers table. The cube root of 8 is 2. X cubed is a perfect cube because the exponent is divisible by my index. The cube root of something cubed is just that something, so x would pop out. Think about it. 2x times 2x times 2x becomes 8x cubed. So that must be my answer. How about the cube root of negative 125, a to the 12th, b to the 6th? Don't worry about this negative because it's underneath an odd root. The cube root of negative 125 is just the opposite of the cube root of positive 125. So since the cube root of positive 125 is 5, the cube root of negative 125 is negative 5. A to the 12th is a perfect cube because 12 is divisible by 3. 12 divided by 3 is 4, so a to the 4th will come out. Again, think about this. A to the 4th times a to the 4th times a to the 4th. You do 4 plus 4 plus 4, which is 12. So that is a perfect cube. B to the 6th, same sort of idea. 6 divided by 3 is 2. And that's exactly what we're doing with our exponents. We divide exponents by the index. So as long as our exponent is divisible by our index, it is a perfect root. Let's try this last one, the fifth root of 32. Ooh, let's look at our table and look at the fifth roots. Now these are the fifth roots. And yep, there it is. 32 is one of the perfect fifths. It's 2 to the 5th power. So when I go back to my problem here, the fifth root of 32, that is nice. It's 2. X to the 5th is a perfect fifth because 5 divided by 5 is 1. Y to the 10th is a perfect fifth because 10 divided by 5 is y squared. So this is nice when they are perfect cubes or perfect squares. When they're not perfect roots, then we have to do this sort of process. So let's review some more of those. Let's look at the cube root of 40, x to the 6th and y to the 5th. I can already see that 40 on my powers table is not in the perfect cube. So I know that this is going to be the type of problem where I'm going to split up into two radical symbols. A cube root over here and a cube root over here. What I'm going to do is put all the perfect cubes right here. All the factors that are perfect cubes will go in the first one. So 40 is no good. And I'm not going to do 4 times 10 because that would be with perfect squares. I don't like 4 right now because we're talking cube roots. I like 8. 8 times 5. 8 is a perfect cube, so that's nice. X to the 6th, well, 6 is divisible by 3, so I can put all of this in here. That's all a perfect cube. Y to the 5th is no good. 5 divided by 3, that's no good. It's not divisible. But I can take 3 of them, y cubed, and that would mean that there's y squared over here because there have to be 5 still. If I took 3 here, there must be 2 over here in this radical. So all of these are perfect cubes, so they should all come out of this cube root. Cube root of 8 is 2. Cube root of x to the 6th is x squared. And the cube root of y cubed is y. Nothing's going to happen over here. That's just going to remain in the cube root, 5y squared. So I've simplified. Let's look at our second one. Cube root of 24. Well, 24 is not a perfect cube, so I instantly know it's going to be a problem where I split apart into two cube roots. So 24 is no good, but 8 is good. 8 times 3. I can see it's another cube root of 8. M to the 6th. Again, that's good. All of it can go right in here. N to the 4th is no good, but I can take 3 of them. I want the numbers that are divisible by 3, so n to the 3rd is good, which means that there must be an extra n over here, the 4th one. R to the 7th is no good, but I can take 6 of them, right? 6 is the biggest number that's less than 7 that's divisible by 3. If I take 6 of them here, there must be an extra one here, the 7th one. Now, if I've done this correctly, all of these should be perfect cubes. Cube root of 8 is 2. Cube root of m to the 6th is m squared. Cube root of n cubed is n, and cube root of r to the 6th is r squared. And this stuff just remains the same. This is simplifying nth root radicals. Let's look at our last one. This time we're talking about a fourth root. Fourth root of 243. Let me go to my table. I don't think 243 is a perfect fourth. Let me slide this over just a little bit. So 243, yep, I don't see it. I see 256, but that's no good. 243 is no good. So I wonder if any of these go in. I think 81 goes in there. I bet it goes in 3 times. Yep, 81 goes in. So 3 to the 4th is 81. So this is a perfect, 81 goes into the 243. So I instantly know, since it's not a perfect fourth, I'm going to be doing this process. So 243 is no good, but 81 times 3 makes 243. So that's nice because that's a perfect fourth. A to the 15th, well, that's no good either. 15 is not divisible by 4. So what's the biggest number that is less than 15 that is divisible by 4? I believe it's 12. And if I take 12 of them and put them here, there must be 3 left over here. Notice that this exponent is less than the index. Therefore, there's no more that could escape into this perfect fourth. B to the 8th, that's good. 8 divided by 4, I can take all of them. And C to the 9th is no good, but I can take the first 8, put them here, leave an extra 1 here. All of these are perfect fourths. The fourth root of 81 from our chart is 3. The fourth root of a to the 12th, 12 divided by 4 is 3, so a cubed. 8 divided by 4 is 2, so b squared. And 8 divided by 4 again is 2, so c squared. And this stuff just remains the same. Maybe do a quick check to make sure all of your exponents, that none of them are bigger than 4. Because if they are, then maybe we could have done some more. Okay, so that's a nice skill to have to simplify nth root radicals. Let's talk calculator. On our calculator, if we're ever using our calculator to approximate, I want you to round to 3 decimal places, correctly rounded to 3 decimal places. So we already know how to square. We actually have a special button for that. That's the x squared button on the calculator. And we should already know how to take a square root that is the inverse of our squared. So we have to push the second button and pull up the square root button. If we want to raise to any other power, the nth power, we like to use that caret button on our calculator. That raises to any power we wish. So if I pull up my calculator, that's the button right here, this little caret button. If I want to raise to any other power, just push that button and then put in your exponent. If we want to take any root other than a square root, that button or that operation is hiding in the math button with a bunch of other stuff. It's down there. It's called the Nth-Root. And it should open up a parenthesis that you definitely want to make sure that you close. I'll just put that in a button thing. It's not really a button. When we go push math, the Nth-Root, it's down here, number 5. They have a special cube root, which is fine if you're looking for a cube root. The Nth-Root is number 5. So it implies that you need to put the index first. So if we were to try to evaluate this, the 7th root of 500, then when I go to my calculator, the first thing I need to push, let me go back to my run screen, the first thing I need to push is the 7, because it's the 7th root. And then I'm going to go push math, and then go down to number 5. Now I'm talking the 7th root. Now I've got the newer operating system, so it puts it up as the index, and my cursor is underneath the radical, so I can put my 500. If you have a lower operating system, then you just put your 500 in parentheses. I might arrow out of there, and there it is, the 7th root of 500. I'll press enter, and I want to approximate this to 3 decimal places. So I've got 429, but to the right of 9 is a 7, which means that the 9 has to go up, but since 9 can't go up anymore, 29 will go up to 30. So 2.430. I'm going to use my approximate symbol, 2.430. Great. And that's how you can use your calculator. Thanks for watching this tutorial on simplifying nth-root radicals and using your calculator for a little bit. I'll see you in class. Bye-bye.